So let's firstly start with the band theory. Isolated silicon atoms containing 4 valence electrons. The valence electrons of an isolated atom of silicon will have certain amount of energy. Similarly, valence electrons of another isolated atom will also have same amount of energy. In this manner, valence electrons of several isolated atoms of silicon will have same energies. But when the atoms combine to form molecule, valence electrons take part in bonding and the electrons of adjacent atom experience repulsion, while electron of an atom experiences attraction from nucleus of adjacent atom. When we consider group of molecules like in solids, the electrons in the outermost orbits will have different energy level. A group of such different energy level constitute valence band. The electrons in the valence band are loosely bound. When certain amount of energy is given to the electrons in the valence band, they absorb energy and go to the conduction band, which has higher energy. The energy difference between the valence band and conduction band is called the forbidden gap. In the case of insulators, the forbidden gap between the valence band and the conduction band is very large. Therefore, the electrons cannot pass from the valence band to conduction band as shown in this demonstration. In the case of semiconductor, the forbidden gap between valence band and conduction band is neither too large and nor too small. Therefore, a very small number of electrons can pass from valence band to conduction band. This is of no practical use. In the case of conductors, the forbidden gap between valence band and conduction band is very small or negligible. Therefore, the electrons from valence band can jump easily to the conduction band and hence conducting electricity.
So we all know about the conductivity of semiconductors, that they lie in the range of 10 raised to power minus 6 to 10 raised to power 4 ohm inverse meter inverse. But if we talk about the practical use of these semiconductors, then it will not be possible as the conductivity is not so large. So if we want to increase their conductivity, then we need to add an appropriate amount of impurity to it. The process of adding the impurity to them is known as doping. Doping, it can be done with an impurity which can be electron rich or that can be electron deficient. So first one is with the electron rich impurity. In the electron rich impurity, the group 15 impurity is added to the group 14 element. Here this 2 rupees coin is representing the group 14 element, that is silicon, and while this 10 rupees coin is representing the group 15 element, that is arsenic. We all know about group 15 elements that they consist of the vacancy 5. In this, the 4 out of 5 electrons will be 1, 2, 3, 4 will be used in making the bonds, covalent bond, while the 5th electron, it will remain free and will get delocalized. So this delocalized electron, it will help in increasing the conductivity of semiconductors, and this increase in conductivity is due to the extra amount of the negative charge. This type is also known as N type of semiconductor. So the second method of increasing the conductivity of the semiconductors is by adding the electron deficient impurity. In this type, the group 13 element is used as an impurity and added to the group 14 element. Here the group 14 element is silicon, that is represented by this 2 rupee coin, and boron, that is the group 13 element, is represented by this 5 rupee coin. In this method, some of atoms of the boron will occupy by some of the sides of silicon atom and will leave a positive hole like this. So the electron from the neighboring silicon atom, it will jump into the electron hole, and this process continues till the electron hole, it will get transferred to the edge of the crystal lattice. So So by this the movement of electron takes place and thus increasing the conductivity. So this is also known as the p-type semiconductor.
Good morning everyone. Today I will explain you the topic magnetic properties of solids. Magnetic properties of a particular material is due to the electrons present in it, as the electrons have a particular magnetic moment, and that magnetic moment originates in an electron due to their constant motion. There are two types of motion that an electron undergoes. First, the orbital motion around the nucleus, and second, the spin of electron around its own axis. And since electron is a charged particle considered as a small loop of current which possesses a magnetic moment. This magnetic moment of an electron is indeed very small. And it can be measured by the unit Bohr magneton, and a Bohr magneton is usually equal to 9.27 into 10 raised to power minus 24 Armstrong meter square. These magnetic properties can be classified into 5 types. Let's get into it in a bit of detail. So now let's study each of the types one by one in detail. First of all, we have paramagnetism. In the paramagnetic substances have one or more unpaired electron, which causes them to be weakly attracted by a magnetic field. These are usually magnetized in a magnetic field in the same direction, and as soon as there is an absence of magnetic field, we remove the magnetic field, they completely lose their magnetism. Few examples are O2, Cu2 plus, Fe3 plus, Cu3 plus, TiO, etc. Next we have diamagnetism. In diamagnetism, all of the electrons are paired. They are usually weakly repelled by the magnetic field, and they are weakly magnetized in the opposite direction. Because all the electrons are paired, then it cancels their magnetic moments and they lose their magnetic character very easily. A few examples of substances can be H2O, NaCl, CH, C6H6, TiO2, etc. So next we have ferromagnetism, antiferromagnetism and ferrimagnetism. Before starting with these types, we should know about the term domain. The metal ions of few substances in solid state are grouped together into small regions, and these are basically known as domains. Each domain kind of acts as a tiny magnet, and in external magnetic field these domains get oriented in a particular direction, which determines which type of magnetic property that particular substance shows. So first of all, we have ferromagnetism. These are strongly attracted by the magnetic field, and these can be permanently magnetized. Why can they can be permanently magnetized is because when the substances which are ferromagnetic are put in a magnetic field, they align themselves in the magnetic moment of theirs align themselves in the same direction, which causes maximum dipole and maximum magnetism, and that stays as it is. Few examples can be Fe, Co, nickel, CrO2. Next we have antiferromagnetism. Example can be MnO, and this happens when the domains are oppositely oriented. Like you can see, one is parallel, then anti-parallel, parallel, anti-parallel, which cancels out the magnetic moment and causes zero dipole. So next we have ferrimagnetism. As you can see the alignment of magnetic moments. So as you can see, there are unequal number of parallel and anti-parallel magnetic moments, which causes an unequal dipole, and it causes it to be weakly attracted by magnetic field. It is weaker than ferromagnetism, but it is certainly stronger than antiferromagnetism. Few examples include Fe3O4, MgFe2O4 and ZnFe2O4. So that will be all for today. Now, I hope you understood the magnetic properties of solids. Thank you.